today we are going to look at polynomial functions and complex zeros. To talk about zeros of a polynomial function first, if you have a polynomial function that's called p of x, if p of a equals 0, then a is a 0 or root of p of x. So you can see those two terms right there, 0 and root, can be used interchangeably. If a is a real number, then x equals a is a z. If a is a real number, then x equals a is a 0 of p. Then x minus a is a linear factor of p for that. One other thing that I'm not sure if he puts in the notes later that you might want to know about this is if a is a real number, x equals p is a 0. It is also could be called an x-intercept. That would be a real 0. Zeros can sometimes be repeated. If you have x minus a repeated n times, then we say that we have a multiplicity of n for that corresponding 0. Typically, we know that the graph of a polynomial passes through the zeros of a graph. However, if a 0 has a multiplicity greater than 1, the graph will behave differently near the 0. So, for example, right here we have the graph of negative 0.01 times x plus 4 times x plus 1 to the third times x minus 3 to the second. And if we look at the multiplicity and the behavior and how that relates, we have x plus 4 as a factor. That means we should have a 0 at x equals negative 4. We have x plus 1 as a factor. That means we should have a 0 at x equals negative 1. And we've got x minus 3 as a factor. That means we should have x equals positive 3 as a 0. So if we would look at each one of those points, at negative 4 right here, we do in fact cross the x-axis right here, just as we would expect to happen here. If we look at negative 1, we do cross the x-axis, but you'll notice here that you kind of have like a squiggle in the graph there. In fact, if we knew a little more, we could call that a point of inflection right there for sure. But it does still cross, but yeah, we've got that point of inflection there also. And then at x equals 3, we touch the y-axis, the x-axis, but it does not cross the x-axis. It just sort of bumps off of that x-axis. We could say that it is tangent to the x-axis. There, it touches just at one spot. So the multiplicity of a 0 here, we're going to see, is going to be the exponent, or you could use the word degree, of its factor. So we would say that x equals 4 just has a multiplicity of 1. If it has a multiplicity of 1, you don't necessarily have to write it. We would say x equals negative 1 has a multiplicity of 3 because that factor is there 3 times since you have an exponent of 3. And we would say x equals 3 has a multiplicity of 2. So notice x equals 3, the multiplicity is 2. The graph is tangent to the x-axis. We could say it kind of looks like it bounces. So this is going to happen anytime you have even multiplicity. So typically we see 2 most often, but it could be if something is to the 4th power, 6th power, 8th power, and so on. If you have those exponents, the graph will not cross, but rather it will just sort of bump off of that x-axis there. Alright, so for each of the following polynomials, we're supposed to determine the degree of the polynomial, find all real zeros, and state the multiplicity of each 0. So to begin with, if we're looking at the degree, if we wanted, we could multiply this out completely to find the degree, but that would take a little while to do. It is going to be easier to kind of look at each x factor that you have. So you've got x to the third right here. Right here you've got an x that is not raised to any powers, but it is going to be multiplied by the x to the third. Right here you have another x, and it is raised to the second power. So what's going to happen here is you're going to have 3 x's here. You'll just have 1 right here, and you'll have 2 x's here, and all of those will end up being multiplied together. So 3, 4, 5, 6. You would have a degree of 6 for this one. It asks us to find each real zero and state the multiplicity that goes with it. So for this part, we're going to be looking at each term here. And so the 3 pieces that we're looking at here, we've got negative 2x to the third. We have x plus 1 is another term. And then we've got x minus 4 being another term. So for this, essentially what you are going to do here is you're taking that part and setting it equal to 0 and solving. Now you'll notice there's a shortcut where you don't necessarily have to do this the long way every time. If I take negative 2x to the third and set that equal to 0, I would need to subtract 2. I'm sorry, not subtract, divide by 2. That'll give me x to the third equals 0, and then I would need to cube root both sides, and the cube root of 0 is just 0. So I get x equals 0 as one of my x-intercepts, or my real zeros here. And this is to the third power, so that would have a multiplicity of 3 for that. The next one I have highlighted in green here, that's x plus 1 equals 0. So that would be x equals negative 1. If we just subtract that 1 from both sides, that is going to have a multiplicity of 1 for that, because you don't have any exponents there for that. So we have an invisible 1 that's written there. And then the last one, we would have to take that x minus 4 and set it equal to 0. That is going to give us 4. And that would have a multiplicity of 2, if we looked at that. So if we do the next part, we have 3 times x squared minus 4 times x minus 2 to the 4th power. Now, this one's got a little bit of a trick to it, because x squared minus 4 will factor further. That is a difference of squares. So we could factor that into x plus 2 times x minus 2. So whenever we do that, we actually can combine these two right here, and we'll have 3 times x plus 2 times x minus 2 to the 5th power there. So looking at this, we're actually only going to have 2 zeros from this one. We have this part right here that we're looking at, and we have this part. Now, we could consider this 3 right here. However, that does not have a variable with it like we had over here for part A. So if I do say 3 equals 0, that's just not true. 3 does not equal 0. There's no variable there to solve for. So that 3 is just a coefficient. It does not affect what your zeros are going to be. Now, if you want, you can write x plus 2 equals 0, which is going to give you x equals negative 2. But it's fine to shortcut that and just go straight to that negative 2, because you can definitely do that part in your head. That one would just have a multiplicity of 1, because it does not have an exponent here. We can put a 1 there if we want. And then we would go over here, x minus 2 would equal 0. So that would just be x equals positive 2. This one would have a multiplicity of 5 there, because your exponent is 5. Okay. Now, c needs to be further factored quite a bit further here, because definitely I can factor an x out of this first expression. I can probably factor both of them further than that. So if I do this, notice I've got x to the third, x squared, and 6x. So I could just pull an x out of that first expression. So that's x times x squared minus x minus 6 there. And I'm going to leave the second part alone for now. There. And x squared minus x minus 6 and x squared minus 7x plus 12 is probably going to factor. So if we try to factor those, we would have an x and an x. Remember, for factoring, we want to multiply to get negative 6, but add or subtract to get this negative 1 here in the middle. So we could do that by doing negative 3 and positive 2. Negative 3 times positive 2 gives you the negative 6, so we can multiply to get that last number. And then if we add them, negative 3 plus 2, we would get negative 1, which would be this middle number here. So that is factored correctly. And then we can also do that for the x squared minus 7x plus 12. So x squared needs to be broken into our first terms. And we're trying to get a positive 12 here and add or subtract to get a negative 7. So that will work if we do negative 3 and negative 4. Negative 3 times negative 4 gives you positive 12. Negative 3 plus negative 4 gives you negative 7. So this is factored correctly. So just kind of to track that, just a little bit of what we've done. This part right here, we just factored out the x to get this piece, and then we factored that second part. So this corresponds all the way down, and then over here, this obviously was the same, and then we factored that into this part. Now, some of those can be combined. We've got y equals x, and I've got x minus 3 and x minus 3 right there. So I can say x minus 3 squared, and then x plus 2 times x minus 4. So if we look at the zeros that go with this, and I am going to kind of shortcut this right here. First of all, this x right here would equal 0, and that would have a multiplicity of 1. I'm not going to list it for the multiplicity of 1 on this one. But it would have a multiplicity of 1. I would have x equals 3 right here, because I'll do x minus 3 equals 0, and I'll move that 3 over. That one has a multiplicity of 2, and then I'll get x equals negative 2, and I'll also get x equals positive 4. So those would be my 4 zeros that I have. One of them right here has a multiplicity of 2. Oh, I did not do the degree on B or C. On B, I need to do the degree. I've got an x squared right here and an x minus 2 to the 4th, so that x will end up to the 4th power. I will have a degree of 6 for this one. Over here, I've got my highest exponent here is the x to the 3rd. My highest exponent here is the x to the 2nd. So I would have a degree of 5 whenever those two things get multiplied together for that. Okay. You should notice here that my degree should correspond with the number of zeros that I have, and he might mention that later. So here for this, I have a degree of 6. I've got 3 zeros right here, 1 here, and 2 here. That's 6 zeros. Here I had 1 0 at x equals negative 2. I've got 5 at x equals 2. And then here I've got 1, 2, 3 zeros here, and then this one has a multiplicity of 2 to give me that degree of 5. All right, so these functions, all the zeros for these are real. So if I graph them, I can see them as x-intercepts on the graph. That is not necessarily always true. Okay, so let's talk about complex roots. Technically, real roots are also complex roots, but some polynomials will have roots that contain an imaginary number. This means that you will not see them on the graph. You can't graph something that has an imaginary number. You should hopefully remember from your Math 3 class that the square root of negative 1 is going to equal I. That's the symbol that mathematicians use to represent the square root of negative 1. And if we have that I in a root, then it's not a real root. So here's a really good example to look at for this. For example, here we've got the graph of f of x equals x squared plus 1. It's just a quadratic that's been moved up 1. And so you can see it does not cross the x-axis at all. So if we want to find the zeros for this, we would set x squared plus 1 equal to 0. And to solve that, we would subtract 1 from both sides. That would give us this x squared equals negative 1. And then we would need to square root both sides. And when we square root both sides, we would get plus or minus the square root of negative 1, which is plus or minus I. So you've got two answers that do make this function 0 here, but you cannot see them on the graph. Because if I do f of I, if I plug it back in, I will get I squared plus 1. I squared is the square root of negative 1 squared. And the square root of something squared, that's just going to cancel each other out. You'll get negative 1 plus 1 here, which will give you 0. I squared is going to equal negative 1. So we get 0. So that means I is a 0 of this function. The same would be true for negative I, right? It really wouldn't change this a lot because negative I squared would just be positive I squared. When you square that negative, it becomes positive. And then you end up with the same thing you had on the last equation. I squared is negative 1. We'll get 0 for that as well. So I and negative I make this equation 0. If they are zeros of this graph, but they're not visible. They're zeros of this function, but they're not visible on this graph. These are complex zeros that we're looking at. So, one really important thing that you have to know, it says key understanding. You might want to put a star next to it here. All imaginary roots come in pairs. Okay? If a plus bi is a root of f of x, a and b just represent numbers here, then a minus bi also has to be a root or a 0 for that function. These are called conjugate pairs that will go together. So I'm actually going to start over here with C. It says determine the conjugate of the following complex numbers. So if you have a 0 of 2 minus 3i, that just means that 2 plus 3i would also be a 0. If I have negative 4 plus 2i, that means negative 4 minus 2i would also be a 0. Notice the first number does not change. It's just that second number, the one with the I, that is going to change signs. Now, let's look at A, because all I have for that is a 4i. I could write this as 0 plus 4i. So if 0 plus 4i is a 0, then that means 0 minus 4i would also have to be a 0. However, we would not normally write it as 0 minus 4i. We would just write it as negative 4i. Basically, the I part is just going to change signs. So negative 4i would be our answer there. In a similar manner, if I have negative I could think of it as 0 minus I. That means positive I would also be 0 for the function. Okay. This next box obviously is a really important concept because it is called the fundamental theorem of algebra, which means it must be pretty important in the world of algebra. And the fundamental theorem of algebra tells us that a polynomial of n degree has exactly n complex zeros when counting multiplicities. So if you have a polynomial that has a fifth degree, it is going to have 5 complex zeros. They may not be 5 different complex zeros. You might have some of them that have multiplicities, but you will have 5 zeros. So here is a picture that they have given us. They tell us the graph of the polynomial function f of x is shown in the figure above. It is known that x equals I squared of 3 is a 0 of f. If f has n degree, what is the least possible value of n? Okay, so we want to know the least possible value of n. So first of all, we need to look at the zeros that we can see from this graph. So from this graph, I can tell that I've got an x-intercept here and also an x-intercept here. Now, pay attention to the behavior of the graph here. at this x-intercept right here, I do not cross the x-axis. I just bounce off of the x-axis. This graph is tangent to that x-axis. That tells me that I have an even multiplicity here for this one. Right here, I have odd multiplicity because the graph actually crosses that line. Now, our question is asking us for the least possible value of n being our degree. So if we're looking for the least possible value of n, then we would assume if I have even degree right here, that this is a multiplicity of 2. That's the very least it could be. It might be 4, it might be 6, it might be 8, but the very least it could be is 2. It has to be an even multiplicity. Right here, I would assume right here my multiplicity is 1. Now, it could be 3, it could be 5, it could be 7, it could be any odd number, but the question is asking me about the least possible value of n. So I'm going to pick the lowest odd number that I can find here. My real zeros, my least real zeros, I've got 3 of them here. I've got x equals 1 has a multiplicity of 2. X equals negative 1 has a multiplicity of 2, and x equals 3 has a multiplicity of 1, giving me 3 zeros right there. It is also known for this particular function that x equals I times the square root of 3 is a 0. So if x equals I square root of 3 is a 0, that would be a complex 0. And I've got 1 right here, but we just wrote down that these complex zeros always come in pairs. So I've got I square root of 3. That means I also have to have x equals negative I square root of 3. So I've got 2 complex zeros here, meaning that I've got a total of 5. So 5 would be my answer here. That's my least possible degree of n. N has to be at least 5. Okay. Okay, the next thing that we're going to talk about is solving polynomial inequalities. So when we write f of x, we are referring to the y value on the graph of f of x. So f of x greater than 0 means that the graph of f is above the x-axis. This is telling me the function is positive. You also might see that the function is positive. So in a similar manner, this f of x less than 0 tells me the function is negative, which means that f of x is below the x-axis. Okay, so if we look at the questions that it's giving us about this graph here, it says, where does f of x equal 0? So f of x is going to equal 0 whenever our y-coordinate is 0. This happens on the x-axis, these points right here where we touch the x-axis. So if you think about the coordinates of these points, this is negative 3, 0, this is negative 1, 0, this is 3, 0. The y-coordinates are 0 there. So those happen at these points. That would be at x equals negative 3, x equals negative 1, and x equals positive 3. Those are places where f of x equals 0. But if I look at a question like f of x is greater than 0, like I see on part B, I'm looking for where the graph lies above the x-axis. So, for example, on this part of the graph is above the x-axis, and this part of the graph is above the x-axis. Now, remember, whenever we're looking at these, we're talking about the x-coordinates where this happened, the domain where it happens. You can think of sectioning it off with those vertical lines. So depending on what type of notation you want to use here, that would be from -3 to -1 if you use interval notation, or if you want to write it this way, you could do -3 less than x less than -1. Notice I used parentheses right here, or I used less than signs here. We don't want to include -3 and -1 because at those points, f of x is not greater than 0, it is equal to 0, so we're not including those points. So that's this first section right here. I also want to include this next section. Here, they didn't put an arrow on the end of these graphs, but we're going to assume that they're probably supposed to be there. They didn't tell us to restrict the domain. So I would have here 3 to infinity, or if I want to write it down here, I could just say x is greater than 3. These are all places where f of x is greater than 0. C asks where f of x is less than or equal to 0. So this time we're looking for where the graph is below the x-axis, which is going to happen here and here. And this time, notice we've got that or equal to sign. So we do want to include the places where our graph equals 0. So that would be -infinity up to -3. Since we can equal 0 here, we want to use a bracket with that -3 this time. Don't ever use a bracket with a negative infinity because you can't actually get to infinity, and you don't want to ever use a bracket with infinity. You always want to use parentheses there. But on this side, we would use a bracket. And then we would also have from -1 to 3 right here. If I want to write that in inequality notation, that would be x is less than or equal to -3, or -1 less than or equal to x less than or equal to 3 for that. Okay. Now, let's talk about what this is going to look like if we are doing this with an equation and not with a graph. So, if we are solving non-linear inequalities, so if you're solving linear inequalities, you can solve them basically like you would solve an equation. But non-linear inequalities or polynomials are going to have to be solved differently. So the first thing you want to do is solve f of x equals 0, which is going to find the zeros of the graph. Then you're going to create a sign chart for the solutions from step 1. You're going to test values and interpret the sign chart. Now that may not make a lot of sense. We want to look for where the values are either positive or negative in step 3 there. It says be sure to write your answer in interval notation and think about the endpoints. So I want to look at this alongside a graph here for this first one so we can kind of get an idea of what is happening here. So if I pull up Desmos, I'm just going to graph f of x equals x minus 3, x plus 1, x plus 4. Okay, and so if I look at this graph right here, you can kind of see what is happening. The first thing it tells you to do is find where f of x equals 0. In order for this to happen, your function has to be completely factored. This one is completely factored. We could not factor any of those terms more. So all we're going to get for those places where x equals 0, f of x equals 0 is just the opposite sign. So x equals 3, x equals -1, and x equals -4. Okay. Now, from the graph, if I'm able to graph it, I can kind of see that's happening here. Right there's my -4. Right there's the -1. Right there's the 3. Those are the x-intercepts of this graph. But from the equation, it is very difficult to figure out whether or not the graph is positive or negative quickly. Now, from the graph, we can kind of see we're positive here between -4 and -1, and also positive from 3 to 0. However, we're going to be doing these. These will be on a calculator inactive section. You'll have to do this without a calculator. So the first thing that we want to do is we want to put these numbers on a number line. So we've got, we want them in order. We want -4 here, we want -1 here, and we want 3 here. And these are the places where our graph equals 0. So they are the places where our graph potentially crosses the x-axis, means it goes from positive to negative. You cannot go from positive to negative or negative to positive without crossing the x-axis. So these have to be the breaking points where we switch from positive to negative or negative to positive. So you have a couple options on how to do this chart. One thing that you can do here is you can just take a test point and plug it into the original equation. So if I'm looking in this section right here, I need to pick any number there that is less than -4. Obviously, -5 is a pretty easy number to pick there. And I'm going to plug that in. I'm going to say -5 minus 3 times -5 plus 1 times -5 plus 4. All right, and so that's -8 times -4 times -1. I really don't care about the value here. I care about whether or not this is positive or negative. So if I do negative times negative times negative, I'm going to get a negative on this section right here. So from -infinity up to -4, my function is negative. Next, I'm going to look at this next section. I'm going to pick a number between -4 and -1. A good one to pick here would be maybe -3 or -2. Let's do -2. So if I plug in -2, I've got -2 minus 3 times -2 plus 1 times -2 plus 4. And so that's going to be -5 times -1 times +2. Now this time, I've got negative times negative times positive, and that is going to give me a positive answer right here between -4 and -1. And it doesn't matter what number you pick between -4 and -1. You could use -3. You could use -3.5. You're going to get a positive answer for anything in that section. We got 2 more sections to check. So if we look between -1 and 3 right here, I'm going to pick a different color. I'm going to pick a number here. 0 is the easiest one to pick right here, but you could use 1 or 2. So you would have 0 minus 3 times 0 plus 1 times 0 plus 4, and that's -3 times +1 times +4. Negative times positive is going to give you a negative answer there. So you got a negative here. And last, we would have to check something above 3. So we're looking at this section here. Let's pick a different color for this, dark blue. 4 is probably one of your easiest there. So if we check that, we'd be doing +4 minus 3 times 4 plus 1 times 4 plus 4, and that is 1 times 5 times 8. All positive numbers being multiplied together, we're going to get a positive right here. Now, if we look at our original equation, we're looking for where this is greater than 0. So greater than 0 is going to be our positive sections right here. So our positive sections are going to happen right here and right here. So from -4 to -1 and from 3 to infinity is what we're looking at. Since we have a greater than sign right here, we don't want to include the endpoints. We don't want to include the points where we actually equal 0. So to write our answer for this one, we would say, just say -4 to -1 or 3 to infinity. All of these values would give you an answer that is greater than 0. So that's the section that is your answer for this problem. Okay, so let's look at the next problem, and I'm also going to show you a shortcut I really like to use. You don't have to use it. You can do exactly like I did example 4 on every problem if you would like, but I do like the shortcut. I'm going to do something very similar to what I did on the last problem. I'm going to find the zeros. So this is going to be x equals -2 right here, and this is going to be x equals 5. I'm going to give myself a little space on this one. and I'm going to put those two on number line. So I've got -2, +5. Make sure they're in order from least to greatest. And rather than just testing points and plugging in for everything, I'm going to take my factors here and put them along this side. I'm going to kind of make a chart. So I've got x plus 2 squared. I've also got x minus 5 right here. And then I'm going to put a line right here for my answer. Okay, now I'm going to draw a chart here like this. And this is a way of looking at this problem just piece by piece, instead of having to plug into every number for everything. So if I look at x plus 2 squared, I'm going to think, what if I pick a number less than -2 and I plug it in? So if I pick a number less than -2, maybe like -3. If I plug it into this, I'll get -3 plus 2. That'll give me a -1. But then I will square it and it will become positive. So I'll get a positive if I plug in a number from this first section. If I pick a number from -2 to 5, like 0, if I plug that in, I will also get a positive here and a positive here. I'm going to get a positive for anything because I'm squaring it right here. So even if I get a negative inside of the parentheses, when I square it, it will give me a positive for this line. So this whole line will be positive. Then I've got x minus 5. So I'm going to think of plugging in numbers. So if I plug in like -3, -3 minus 5 will give me -8. That'll be negative on that section. Then I will do -2 to 5. I'll pick something between here, like 0. If I plug in 0 right here, 0 minus 5 still gives me a negative number right there. And then if I pick a number bigger than 5, like 6 or 7, if I do 6 minus 5, that gives me a positive number. So I have a positive right here. So essentially what you're doing is you're just looking at each piece individually about whether or not it's positive or negative. You can do this a little more quickly if you're just looking at one piece. You should also notice that in cases where your sign is going to change, so like right here I've got x minus 5, whenever it changes at the 0 that corresponds to that factor. So the 0 that goes with x minus 5 is x equals 5, and notice that we changed from negative to positive at that point, and that should always happen if the sign changes. So now if I look at this, for the numbers here, I've got a positive number times a negative number, which is going to give me a negative. I also have a positive number times a negative number here, which still gives me a negative. And I have a positive times a positive here, which gives me a positive. So if I look at the original problem here, I've got a grade of less than or equal to 0. So I'm looking for the sections that are negative. So on this answer line, I'm looking for negatives, this section and this section. Okay. So I could write it this way. I could do -infinity to -2. Because this is or equal to, I would use a bracket, and then I would go from -2 to 5, and I would use brackets for that as well. However, you're not going to see an answer choice look like this because that -2 is being repeated. The easier way to do this is just do -infinity all the way up to 5 with a bracket there. Now, if I had a less than sign right here instead, I would need to use parentheses, and I would need to write it that first way, but with parentheses. Okay, so any number less than 5 is going to give you a negative answer for this. Okay, the last thing that we are going to look at for today, I'm going to save this part right here since we're having to do this on a video. I'm going to save that last page for you guys to look at tomorrow whenever I'm hopefully here. This video is already getting long. So determining the degree of a polynomial given a table. So if given a table of values with equal width input intervals. So we were talking about this the other day. Equal width input intervals. Remember, your input is your x most of the time. we're talking about the x is going up by an equal number. We can determine the degree of a polynomial by examining successive differences in the output values. The number of successive differences needed for the differences to be constant is equal to the degree n of the polynomial. So we have really already done this with linear and quadratic. Something that is linear has a degree of 1. So whenever we look at the differences on the table, we're going to see that it only takes one time and they become constant. A quadratic, we have to look at the differences twice. It is a degree 2. Okay? This continues to be true. If we have a cubic, we'll have a degree of 3. It'll take 3 differences. So let's look at this problem that we have here. The first thing you must always check is make sure your x's are of equal width. So we're going up by 2, up by 2, up by 2, up by 2. So these are equal width intervals, and we can make assumptions based upon this table and the differences that we see. So if we look from negative 2 to negative 3, that is a decrease of 1. From negative 3 to negative 1, that is an increase of 2. From negative 1 to 4, that is an increase of 5. And from 4 to 12, that is going to be an increase of 8. So this is not a constant rate of change because those numbers are different. We need to look at the difference again. So that was our first difference. We're going to do this again. So from negative 1 to 2, that is an increase of 3. From 2 to 5, that's an increase of 3. And from 5 to 8, that's an increase of 3. Which we kind of have already done this, as I said before, because we would have said, oh, that's constant rate of change on your second differences, so this is quadratic. A quadratic has a degree of 2. So this would be degree 2 right here. Let's look at the next problem. First, we must check to make sure we're increasing by equal amount intervals, and you are in fact going up 3 on your x's every time right here. So, okay, so we see that this increases by equal width intervals, so we can look at our differences. So from negative 2 to 0, that is up 2. Then we go up 10, up 17, and up 23 here. So definitely we do not have a degree of 1. We need to do this again. We'll switch colors. Let's do it again. So from 2 to 10 is up 8. Then this is up 7 and up 6. So that number is not constant. So this is not a second degree polynomial, but you should start to see, oh, I think we're going to have a pattern on this next one. So from 8 to 7 is down 1. From 7 to 6 is down 1. And now we have a constant rate of change. So on this particular graph or table, we would say that the degree would be 3. Now, of course, it's possible to have tables where this does not happen at all, and then it would be neither. You wouldn't be able to tell the degree from the table. But if you're being asked for the degree, you should be able to eventually get to a constant rate of change for that. I'm going to stop here on this video because it is already getting very long. We will talk about even and odd functions whenever I'm back, because if you're watching this video, it means I must have had to be out of school today. So work on the assignment, and we'll go over any questions you have whenever I'm